Good morning and welcome to the Blue Waters webinar series. I'm Maxim Belkin with the Blue Waters project at the National Center for Supercomputing Applications at the University of Illinois. And today it is my pleasure to welcome you to a new webinar in our scientific workflows track. Our speaker today is Johannes Koster, a computer scientist and a group leader in the Algorithms for Reproducible Bioinformatics group at the Institute of Human Genetics, University of Duisburg-Essen in Germany. Johannes is the founder of a popular distribution called Bioconda and a lead developer of Rust Bio. He earned his PhD in computer science from the University of Dortmund. Currently, he leads the group that works on a number of tools for computational science. And one of these tools is called Snakemake, and he will present to us today. Before we begin, I'd like to remind everyone that you can ask questions on YouTube using chat and using our Slack channel. Information on how to join our Slack can be found in the sidebar. With that, I'd like to thank you for joining us today, and I'll turn it over to Johannes.
Thank you. So thanks a lot for the organization and for having me here. And so let's start with the webinar. Snakemake is a workflow management system that is around since already 2012, and by that has become quite mature and has a large community of users and developers. So it has by now over 100,000 downloads on Bioconda since 2015, and among that alone 50,000 downloads came in the last year. So it's really even a growing technology since. And it's faster and faster growing and adopted by more people. And it has been used in a lot of high impact publications among all the big journals, actually, in order to ensure reproducible data science. And so let's talk a bit about reproducible data analysis. So usually when you're thinking about data analysis, you're looking at some kind of data set, and then you apply various transformations, filtrations, aggregations, and visualizations in order to obtain your final results. And these results can entail tables, plots, figures, whatever you put in your scientific paper in the end. And usually you don't do that on a single data set, but on tens or even hundreds or thousands of data sets, and you have to repeat all these steps. And of course, it's not a good idea to do that by hand if you want to have it reproducible, because then you will fail in documenting what you did actually, or it's harder to redo parts of the analysis if some parts of the raw data change or things like that. So therefore, it's good to have some kind of formalization that allows you to automate these analyses. And in order to get a data analysis reproducible, you have to actually consider 3 dimensions. The first dimension is, as I said, automation. So you need a system that allows you to go the whole way from raw data to the final figures or tables of your paper while documenting all the used parameters, tools, and versions. And you need to be able to execute all these steps without manual intervention, actually. And the second aspect is scalability. So if you go from a few or a handful of data sets to hundreds or even thousands of them, you need to be able to use a system that handles parallelization for you and allows you to effectively use the available resources on any computing platform that you might want to use for your analysis. And finally, a very important aspect is that the data analysis is not only just the code that entails that is contained in the analysis itself, but it's also about deploying the software stack that you need for each step to the actual system where you execute the analysis. And this, in order to have a reproducible analysis, this needs to be kind of part of the analysis itself, or the framework that does the analysis for you has to handle that for you as well in order to have it in a portable way. So one system to deal with these kinds of problems is Snakemake. And Snakemake works by defining your data analysis as a workflow in terms of rules. And each rule represents thereby a step in your analysis. So I will come later to the details of rules, but the key idea is that you like split your workflow up into these rules. The rules have input files and output files, and Snakemake determines the dependencies between these, and by that generates a directed acyclic graph of jobs, which represents what steps needs to be done in the analysis. And independent parts of that graph can be executed in parallel automatically by Snakemake, and it has a very flexible scheduling mechanism that allows you to scale your workflow to any underlying computing architecture without needing to modify the workflow itself. And to give you more insights into that and really give you a feeling about what that all means, I will now start with a live demo about Snakemake. And this live demo, let me go back a second, is actually also available via this link here at the bottom. So if you like, you can follow me just right now and doing exactly the same things as I do, or you can do that later on. So this link leads you to like a Docker-based virtual environment in the browser where you can do all the things that I do now. Okay, so this live demo uses an example from bioinformatics, but you actually don't need to be a bioinformatician or biologist in order to understand that, because, well, we use an example analysis from that field, but all the steps are general enough so that you should be able to just abstract the biological details away. And I will try to give you like some hints for generalizing what we do there. Okay. So what is the setting? So the setting is that we are in genomics, where we are trying to assess the genome of one or more patients, for example, in order to determine what kind of tumor they have or something like that. And for this, there exists a technology that is called sequencing, DNA sequencing, which allows you to retrieve small snippets of the genome of a patient. And these snippets then have to be mapped to something that's called a reference genome. So this is basically something that computer scientists would call pattern matching. And then we do some kind of transformations on these mapped sequences. And finally, we do some aggregation and obtain some features out of these. And finally, we want to do some kind of visualization. So this is the setting we are in here. And for those bioinformaticians among you, so we will map reads with a read mapper. We will sort them. We will call variants on them, and finally we will plot the qualities of the called variants. But this is all not important to really understand if you just want to understand Snakemake and don't care about bioinformatics. Okay, so if you're not a bioinformatician, just think of this as we are doing some kind of transformations, aggregations, and filtrations on an arbitrary data set. Okay, so let's start. How would we do that with Snakemake? First, whenever you start doing an analysis with Snakemake, you have to create a central file that is called a snake file. And this name actually comes from the fact that Snakemake inherits a lot of properties from the famous Genome, which is like a famous build tool for C, C++ libraries. And there, the central file is called makefile, and therefore Snakemake, in Snakemake, it's called snakefile. But anyway, so this snake file defines basically your workflow in a textual way. So Snakemake provides a domain-specific language that allows you to define these individual steps of your workflow. And this domain-specific language is, in fact, an extension of Python. So that's important to know. So anything I write into the snake file could be first just plain Python code, okay? But it's extended by special syntax that allows me to define workflow steps. And this is what I do now. So let's start with the first step of our data analysis, which is mapping reads to a reference genome. Okay, so how do we do that? We write something that's called a rule. Every rule in Snakemake has a name. In this case, we could call this map reads. And then every rule can have a set of input files and a set of output files. So in this case, we have some data already available in this directory where we do the live demo. So we have this file genome.fa, which is a so-called reference genome where we want to map our short sequences against. So we will first refer to that genome from this rule. And the second file we want to use is one of our actual raw data sets. And these are available in this so-called FASTQ format. But again, if you're not a bioinformatician, don't care about this format. It's just some kind of raw data set. So second part of the input files would be then a path to one of these data sets. Okay. So then we want to have some kind of output file. So this rule shall take these input files and create something. And in terms of this data analysis, it will create a file in the so-called BAM format. So the suffix is BAM here. And it should have the same name as the input data set here. But that's just in this case. Okay. And finally, we need to tell Snakemake how to create the output from the input. And for that, it allows you to define, for example, a shell command. So in case of a shell command, you would usually invoke some kind of command line tool that generates the output from the input. In this case, this is the tool BWA. It has a subcommand mem, and it takes exactly the two input files we give here as input. And as you can see here already in Snakemake, you can refer to input and output files from shell commands via having this braces notation here. So anything inside the braces is mapped to the properties of this rule, in this case, input or output. And if an input directive like here has multiple files specified, like here we have 2 files, Snakemake will automatically concatenate them via a white space, so that here we in fact have actually something like this. Okay, but we don't have to write that out. This would not be very flexible. Instead, we can just refer to it like that. Okay. Now, in this special case, again, nothing you should be interested if you're not from the field. We have to pipe the output into another tool called SAMTools, which has a subcommand view, and then we need to give it some parameters. And finally, and importantly, we want to write to this output file we have here in the end. So we can do that via piping the output of this SAMTools command into whatever we define here as a file name for the output file. Okay. So this would already be our first step in the data analysis. We have defined an output file, we have defined 2 input files, and we have a shell command to generate the output file. However, as you remember from my initial slides, in order to get this reproducible, we are still missing one dimension, which is the portability. So if we use it like that now, we would need to install BWA and SAMTools in order to be able to execute this properly. And in order to get this really reproducible, we need to ensure that people use exactly the same versions as we intend them to use. And of course, you could write all that down in a README file, like install BWA, install SAMTools in this and that version, but that's not really a scalable solution. So what modern workflow management systems, Snakemake is not the only one actually to do that, offer is that you can integrate the definition of the software stack for each step of the workflow within the definition of the workflow itself. And in case of Snakemake, this is possible via the so-called Conda package manager, which directly integrates with Snakemake. And we have a special directive for that, which is called Conda. And from that directive, we can refer to an environment that we give some kind of name. And this environment is defined in YAML format. And we can now define this environment in an additional file. So first, let's create a new folder. And inside of that folder, We create a file mapping.yaml. And this file has the following syntax. So first, it defines so-called channels, and these channels represent sources where the Conda package manager shall retrieve the packages from. And two of these channels that are usually very useful in this scenario are Conda Forge, which provides general purpose packages from open source field, and second is BioConda, which is specialized on bioinformatics packages and builds on top of Conda Forge. And now the second part of this software stack definition, let's call it like that, is that you define the dependencies that you actually want to install. And in this case, this is obviously the tool BWA and the tools hand tools. But it's not only that you give it the names, but for having it reproducible, you should allow Conda to install a particular version, those versions where you tested the workflow for. And you can do that by just specifying like the version number here after the name. You can do it like this. So what this means is that Conda, the Conda package manager, will take this environment definition and create for you, given that you have installed Conda on your system, create for you an isolated software environment with just these two tools in it. No side effects to the rest of your system. It won't affect the rest of your software installation on your system. It won't affect other projects and won't even affect other steps of the same workflow. So this is really isolated for that particular rule. And by that, you ensure that it's kind of reproducible, does not have side effects on older projects and the rest of your system. Okay, so with that, we could already like start our workflow. So let's just do that. So for executing a workflow, Snakemake has a command line interface. So it's just the command Snakemake. And it has a dry run functionality. So you can always start it with -n for just having a dry run. And you can give it a target file that it shall create. So Snakemake always goes from like targets to what it actually has to do. You provide Snakemake with a target, and Snakemake finds a composition of rules to generate your target. So let's do it like this. You see here is Snakemake printing a plan of what it would actually do. So it prints here the rule name, input and output files, and some statistics about what rules it will actually execute. And of course, this is now, since we only have a single rule, this is a bit boring, the output. Okay, but it's not only that we run it like that, but we need to tell it additionally to use the Conda integration in order to tell it that it shall actually deploy the software stack for us and before executing the rule. So if we run it like this, let's do that. Snakemake will first download the required software via Conda and install it to such an isolated environment. And this will take some time, and once it's done with that, it will actually execute the rule. So while it's downloading, let's have a look at the rule again. This is kind of course, a bit not so useful rule, because currently it's specified for a single sample, and it has to be like an input file that's called a.fastq, and the output file has to be called a.bam. So now think about this initial figure on my slides again. You, of course, don't want to do this step for just a single data set, but rather you might want to scale it up to tens or even hundreds of data sets. And for that, Snakemake provides you with the ability to specify wildcards in input and output files, which are then replaced by whatever values you need. So in this case, we could write something like this. See these braces here, and this means to Snakemake that this part of the output file pattern can be replaced by any non-empty string. And once it has determined what string it has to put in here to generate a certain target file, it will propagate this information or this value of the wildcard to the input files, and by that it will know, okay, so my input file has to be called like the same but just with another suffix, in this case fastq instead of bam. Okay, so now let's see if this works. So actually, as you can see here, it's already done with that first rule. So it has done some things and created that file. So if we now look into the folder mapped, we see that there's actually this file created. So what this did is just like transforming our data set while kind of annotating it with additional information. So this would be the general story here. Okay. Okay, so let's see what happens if we try to make use of this wildcard now and create the same file, but for a different sample name. So we can write -n again, tell it to use conda, and then we request not a.bam, but we request b.bam, like this, okay? So if we do this, we see that it fails. What's going on here? Oh, I didn't save it, so let's try again. Okay, here we go. So once I save the file, we actually see that Snakemake will now create like a second job from the same rule here. And in this case, it will put b in here for the name of the wildcard. And it will want to create the file mapped /b.bam. And as you can see here, the value of this wildcard sample is propagated to the input file, so it requires the file b.fastq to be present in the samples subfolder. Okay, so if we now run this, you will see that it starts immediately mapping the reads, so doing its transformation without needing to download the conda packages again and creating the environment again, because obviously it will use the environment that it created before. So it's smart in this sense that you don't need to redo this conda installation every time, but it just reuses environments that you already initialized before. Okay, so this is already the first step of our analysis. Let's go on with the next step. So the next step is just a simple transformation of the data set that we created here. So for those aware of what is done in genomics, we are actually sorting the mapped reads by genomic coordinates. For the rest, we are just transforming our data set. Okay. So now we take this input file here and we modify it by transforming it somehow. And we store the results in a file named the same, but with the prefix sorted here. Okay. So again, we tell Snakemake how to do that via a shell command, and we can make again use of this samtools command here, but in this case we use the subcommand sort, and sort has some parameters. Just tell it to sort the input file and write the output to whatever you specify here. Okay. Again, this would not work if we didn't have samtools installed, so we can get rid of this problem via just again using conda integration of Snakemake. So since if you remember what we defined here in this environment, this mapping environment already contained the samtools command, so we can just reuse that environment. So important message here. Although you specify an environment for every step, you can of course share environments between steps via specifying them like in several rules. Okay. So that's it already. We can just try to go on, like for sample A again. This time we want to have it sorted. Okay, let's do a dry run first. So what does Snakemake want to do? It just wants to do the sorting. So because mapped a.bam is of course already there. So it won't ever redo any computation if the files are already there and if the files are up to date. So what does up to date mean? So Snakemake, before executing anything, is checking whether the output files are actually newer than all of the input files. So in case of the file a.bam in the subfolder mapped, there's nothing to do because the file is already present and none of the input files has a newer modification date than the file a.bam. Okay, so therefore it doesn't need to redo the mapping here. But we could force it to do, so there's a command line flag -r. We could give it a name of a file or a name of a rule. So in this case, we could give it like the name of this rule. And if we do that, you will see that Snakemake would want to execute two steps, like mapping the reads, generating the file a.bam, and then sorting them, using that file, and afterwards creating this file a.sort.bam. And it also has the ability to like tell you what it actually wants to do. So there's this flag -r or --reason, and then Snakemake will print like the reason why it would execute job. So of course, in case of mapping, the reason is that we force it via the command line now. And in case of the sorting, it will print us like two reasons. First is that file mapped /a.sorted.bam is still missing, like in our working directory, so it's not yet there. So obviously, therefore, it has to run the rule. And second is that another job during this execution, in this case, this map reads job, will update an already present input file. So therefore, of course, it has to rerun this rule as well. Okay, so let's just do it, removing the dry run again. And as you can see, it starts again immediately doing all the steps because Conda is already done. We already have that environment and the software is already deployed to our system. Okay, so now we have kind of applied two transformations to our raw data set. Now comes something new. So now we want to do an aggregation. So we want to aggregate over multiple samples, obtaining some kind of extracted features. In order to aggregate, we need to first tell Snakemake actually about all the samples that are present. And this is an important thing to know about Snakemake. So Snakemake will not work in the sense that it looks at what is available in your directory and then applies whatever rules it knows just blindly to the files in the directory. Rather, the way Snakemake works is that you always give it like what you want to have it in, what you want to have in the end, like the sample names or whatever. And this usually works via something like a sample sheet in reality, so where you really have a table with all the information about the data sets or samples you want to look at. But in this simple case, you can also make use of the fact that, as I said initially, Snakemake is a domain-specific language on top of Python. So that means that anything we write here outside of the rule definition can be plain Python code. So here at the top, we could write some SQL query to like obtain the sample names. We could parse a config file. We could read a table with pandas and so on. But we can also just define a Python list, which we do now for the sake of this example. So we can say, OK, our samples are A, B, and C. That's it already, just plain Python. So this is only Python code here. And this variable is now just a global variable that is available in this workflow. And we can now use that variable to do our aggregation. Let's see. So this third step, for those familiar with bioinformatics, will be the step of doing variant calling on the mapped reads. So we have a rule call. This rule has some kind of input files. So first of all, it has like a genome, which is the reference genome. Again, the same path as we have here at the top. So data/genome.fa. Okay. Second part is that we want to have the BAM files. And we want to have those that are sorted already. So this is not enough because here we have a wildcard and we need to aggregate over all the values of that wildcard. So Snakemake has some facilities to help you here. First, again, thinking about this is just plain Python, we could write something like this. Okay, so for those of you knowing Python, this is just a list comprehension over the list samples that we have defined here at the top. And for every element of that list, we format this string here by replacing the wildcard sample here with the value of the particular sample in the list. And by that, we would get like a list map/a.sorted.bam, map/b.sorted.bam, map/c.sorted.bam. But this can become cumbersome if you have larger workflows and maybe a bit less readable. So Snakemake has a helper for that, just for this particular use case, which is called expand. And you can write it like this. So this just tells Snakemake, like do exactly this list comprehension we have seen before. So replace the value of this wildcard sample by every value that you give here in the keyword argument. Okay, and this helper is kind of flexible in the sense that if you have multiple wildcards in here and specify multiple values here in the keyword arguments, it would automatically do the product for you. So this can be handy when doing aggregations. But you're not limited to these kinds of aggregations because you can use arbitrary Python code to aggregate over files here. This is one of the key strengths of Snakemake. Okay, so these are our input files. Now coming to our output files. So as output, we will just have a single file containing all the variants that are extracted out of these aggregated data sets. So for those of you not from bioinformatics, we are just doing now an aggregation together with some kind of feature extraction, and we write the aggregated features into this output file here. Okay. Again, we are using a shell command for this. And this shell command, in fact, again, uses this samtools thing, in this case, the mpileUp subcommand with some parameters. One of them is the input file. As you can see here now for the first time, we're not only able to access like all input or output files with like one of these declarations here, but we can also access individual input or output files if we specify them like this with a name before the file, and then we can refer to that name from this braces syntax. Okay. Second file we need to put in here is the BAM file. And then the result is piped into another tool that's called BCF tools. Just subcommand call. We give it some parameters again. And finally, the output of BCF tools is written to our output file that we define here. As you can see now, this command would be a bit too long to put it in just one line. So we split it up into 2 lines here. And this is just a special like property of Python. So if you have 2 strings that are only separated by white space, Python will automatically concatenate them into 1 string. So this is in fact the same as if we would write it like that. But in this case, we would just reach beyond the 80 character limit. So therefore, we split it up into 2 lines here. Okay, so again, this one needs some kind of Conda software environment stack. So we define ourselves another environment here called calling.yaml. Create that environment. Let's help ourselves by copying the original one over. We don't need BWA in this case, but we need BCF tools at version 1.7 as well. Okay. That's it already. Okay. So now we have a rule that aggregates over multiple samples here. Okay, so let's try to tell Snakemake to create this file. First doing a dry run again. So what happens here? You see in the end, it wants to run this rule call, okay, with all the BAM files. and the genome and generating one single output file. But in order to do this, it has to create other files as well. So it has to map our reads from, it has to sort our reads from sample C. It has to map the reads for sample C. It has to do the sorting for sample B. Okay. So you can see, again, it doesn't do the entire computation. So for example, no mapping for sample B, no mapping for sample A, and no sorting for sample A, because those files are already there and they are already up to date. So no need to redo this. What you already see is that like Snakemake is trying to be trying to avoid redundancy whenever possible, which can be very handy if you like iteratively build a data analysis or if you add samples later on and so on. So no need to redo all things over and over again. Okay, so let's tell it to start. Again, it now has to create this conda environment for the variant calling that we defined here. So it will download these two packages and deploy them into an isolated environment, and then go on with the individual steps. Okay. So you see that it already starts sorting, calling, and then it's done. Okay. So now we already have our variant calls, and let's just, for fun, have a look at them, because they are kind of human readable. So as you can see, now we have this file here in VCF format. And there you have like the features that the calling process extracted from our data. So basically, it defines the chromosome, the position within the chromosome, like the position on the DNA, and then it defines what kind of nucleotide in the DNA was replaced. So this can mean that you have a mutation in the individual genome of a patient compared to other patients, or in this case, a variant compared to the reference genome, and so on. Okay. So, but for non-bioinformaticians, we just have some features extracted here. And these features have a special column here called qual, which basically shows you the posterior probability for this to be actually a true call, okay? And this is scaled in some kind of scaling called Fred scaling. So it's kind of a special log scale, basically meaning the higher this quality is, the more sure the caller here is that this is a true variant. So this is a true signal and not noise. Okay, but that's all not so important. The important thing is here we kind of want to generate some quality control plot over this column, giving us like the distribution of the quality scores. So meaning with Snakemake, you're not limited to these shell commands. You can integrate into the very same analysis also steps like plotting, visualizing, and so on, using scripting languages. And we will do one example for that now. Okay. So let's have a rule called plot qual. It has some kind of input data again. In this case, we only need this VCF file. Has some kind of output data, and in this case this would be our plot. So usually it's best practice to have a subfolder plots for all your plots. You can have, of course, even more subfolders. In this case we don't need more subfolders, so just quals, and then this can be in PDF or an SVG, whatever you like and need for further inclusion in your paper, for example. Again, we need a conda environment in order to get this reproducible. So this conda environment we could call, like, for example, plotquals.yaml, or what usually is advisable in case of things like plotting. Usually you will use this environment for a lot of rules when you do more plots. So let's just call it stats.yaml. Okay. So now we don't need a shell command, actually. So of course we could write something like this, Python And then we would have a script called quals.py in the script subfolder, and then we would give it some kind of arguments like input and so on, and maybe even some parameters and so on. But this is all not needed with Snakemake. You can have it much simpler. Just the path to the script, and here you use the script directive. Snakemake will recognize that this is a Python script just by the file extension, and it will handle it in a special way, and we will come to that special way in a second. First, let's look at the Conda environment first. So let's create another environment again, stats.yaml. So that's channels. We have again the same channels, Conda Forge, BioConda. Now we define some dependencies. So we want to do dependencies. So we want to do plotting with Python. Obviously, the tool of choice is matplotlib. Okay, in this case, we will use version 2.2. Second thing we need is a tool to read the VCF file. So this file containing our special features, genomic features. So for that, we will use the library pysam. Let me look up the version. There we go. And then with these scripts, it's usually a good practice to specify like a Python version, because sometimes Python syntax changes, and you need to be sure that your script will run with a particular version. And this is not subject to change at the time when the user invokes the workflow and the environment is created. Otherwise, Conda would always use the newest Python version, and something that you use in your script might be deprecated at that point or something like that. Okay. That's it for our plotting environment. And now we need to generate the script. So first, create a new folder. And inside of this folder, we create a file plotwalls.py. Okay, first some boilerplate. So we need to import matplotlib. And here, important, if you want to have your workflow portable and be able to execute it on your local machine or on clusters or servers and so on, it's important to tell matplotlib to use a certain backend that does not need an NX server, so a graphical environment. So we usually do that via specifying this agg backend. Okay. And now we can say from matplotlib like this. So we import the PLT object from matplotlib, and then we need to import the functionality to read the VCF file. Like this. Okay, so now we can start writing our script. So as I said, we wanted to extract this quality column from the VCF file. So the variant file or the VCF file can be read with this class we just imported here. And this just expects a path to that file. So of course we could now write like the path in here, like what was it, call/all.vcf. But this is of course not really scalable, and so you would need to change the path here and here whenever you change something to the layout or whatever. And luckily, Snakemake allows you to directly use the properties of your rules, which define a script directive, from within the actual script. So what we can do is the following. Snakemake inserts, before executing the script, a special object called Snakemake, And this object has an attribute for every property of the rule. So for input, output, and so on. So we can use this attribute like for input and access the first input file, which is exactly this file here. So no need to specify the string again. No need to set up a command line parser. No need to set up any kind of boilerplate code. We can just directly use the properties of the rule. And Snakemake will make sure that this object is actually available like inside the script by inserting it like dynamically here before executing the script. Okay, so this is our VCF file, and we can now iterate over that file for record in the variant file. And now for every record, we want to extract the value of this quality column. And for this, PySam allows us to write the following record.qual. And we put the entire thing into a list comprehension and save this in the variable quads. Okay. And now we can plot just a histogram of these. So plot hist quads. And finally, we tell matplotlib to save this. And again, we need a file name now. And of course, I don't want to retype the file name that is defined here, but I rather just access it from the properties of the rule. So again, same pattern, snakemake.output.0. So we get the first output file here. And if this file would have a name, so if we would name it like this, which makes sense only if we have multiple files here, then we could, of course, not use an index here, but rather use the name here. Okay. So that's it for the plotting already. So as you can see via the script directive, Snakemake allows you to like directly integrate into your whole analysis whatever downstream post-processing and visualization steps you have or need to do for your analysis without any boilerplate. So it's very simple and straightforward to write these, and thereby like making it easy to integrate new steps into the workflow without a lot of effort, and making it easy to do this modular. So not having one giant script creating all your plots, but have many single rules, and thereby have a nice overview of what you actually do just via looking at the workflow itself and not having to look at the giant script containing all the plots and so on. And this makes all the workflow very, very human readable and accessible. Okay.
Johannes?
Yes.
We have a question.
Yes.
So the question comes from Francisco on YouTube. Do you see Snakemake being used for creating complex pipelines outside genomics? If the case, do you see the syntax being easily portable?
Yes, it's done. I mean, it's used in a lot of fields outside of bioinformatics. It's even used in companies so it's not tied to genomics at all. So although the initial publication was in bioinformatics, it's very generic. So all these things that I've shown you so far, just exchange the shell command with something completely different, or exchange the script here with something from a completely different domain, and it will still work. It's only a framework that allows you to formalize the steps of a data analysis and allows you to do this in a reproducible way. So it's completely independent of the field.
Thank you.
Okay, so now we have this kind of plot. So just some kind of plot, nothing special about bioinformatics, and we tell Snakemake to create it. So again, we give it a target, plots walls.svg. Again, we tell it to use conda. Let's do a dry run first. As you can see now, since it has created all the other files already, it just wants to do this rule for the plotting. So let's do it. And while it's downloading Python 3.6, which will take some time, let's look at the entire workflow from a more broad perspective. So we have all these steps here. And as you have seen so far, Snakemake, I've always invoked Snakemake via specifying like here a target at the command line. Okay, now this is of course not how you would do it in practice, because usually, like in the end, at least, you design your data analysis in a way that somebody just needs to execute it, and it will create all the plots and figures you intend it to create. Okay, so we want to tell Snakemake like what is the default target, so that the user does not need to specify the target at the command line all the time. So Snakemake allows to do that by the following paradigm. So when you don't specify a target at the command line, so if we just invoke Snakemake like this without a target file here, it will try to execute the first rule. And this rule then like recursively requests other rules to be executed because certain input files need to be created and so on. And we can use this property to tell Snakemake what is our default target. This is actually similar to GNU-make for those of you who know GNU-make. So we just define a rule here with some kind of name. Usually you name it like all for saying that this is all you want to create in the end. And it just has some input files. In our case, we want to have the extracted features like this. And we probably want to have this plot here. Okay. Like this. Okay. So this rule does not have an output file. It does not have a shell command or a script. It just has input files. So now if we try to invoke Snakemake without any additional files here, it will see, OK, this is the first rule. So I want to execute this first rule. In order to execute this first rule, these two input files need to be present. So it will try to find a composition of rules to generate these two input files. So it will determine, OK, in order to get these files, I need to run the plot qual rule. I need to run the call rule. And then for those, again, recursively, what files do I need? OK, this data/genome FA is already present in the file system. We have it here. But I need this map/sample.sorted.bam for each of the samples here. So I need to run this sorting rule. I need to run this mapping rule, and so on recursively. OK, so by that, you basically generate the entire graph of jobs. So of course, if I would run this now like that, it will tell you that it has to do nothing. As you can see here, nothing to be done because we already created all these files. So this will also tell you, OK, everything is done. We could now tell Snakemake to re-execute everything. So there's this force all directive at the command line, which will tell Snakemake to just do everything again. And if you look at the workflow now, you see, OK, we basically do the entire thing again. OK. Yeah, so that's basically it for the most simple use of Snakemake that is currently possible. Now I want to give you insight into some extra features that it provides. One important aspect of data analysis is, of course, data provenance, so that you are able to keep track of when were files created, what was used to create these files, and so on. And for this kind of stuff, Snakemake allows you to create automatically, without further ado, reports. And for that, it has just this command line flag report, which creates your report. And this will just leave a file, report.html, as you can see here. And if we open that file in the browser, we will see what actually the workflow was about. So first we see like the graph of jobs or the graph of rules. So the rule that was applied first, then the second, the third, the plotting, and finally our like artificial target rule here in the end. For each of the jobs that actually run something, we will see a runtime. In this diagram, we see when the actual files were created. And we also have a table where we can see like the individual output files of each rule. So for example, for the sorting, we see that this actually was applied to create 3 files. And importantly, for provenance, for each step, we see what was actually the software that was used. So this is basically just replicating the contents of the Conda environment, as you can see here. Okay, so as you see it now with this example data, this report looks a bit empty, which is of course natural since the example is quite small. But it's also because we didn't annotate it with further information. But you can use these reports not only for like collecting the provenance information, you can also use these reports to deliver results, or even something that would be a textual description of your data analysis that could directly go into your manuscript. Okay, and for that, it's possible to annotate output files of rules with a flag called report, like here. And this flag is taking a keyword argument caption. And this points to some kind of file. So let's create that file. This file is in restructured text format. So that's just like Markdown, but a bit more involved, a bit more powerful than Markdown. And so basically, Snakemake, upon this directive, when it detects that during execution of this report command, it will include this output file into the report and add this caption text that is stored in this file into the report. So let's see how that looks like. So first we create the missing file, report. So this is a histogram of variant quality scores. Okay, so this would be some kind of caption. Importantly, these caption text here is not limited to just write plain restructured text. We can, similar to the script directive of Snakemake, which allows you to assess properties of the rules, you can also access the properties of the rules from inside these restructured text syntax via using the templating engine Jinja. So we could say something like this, and then we access some wildcard in here. So in case the wildcard contains some parameter of our rule or something like that. Okay. But in this case, with the plotting, we don't need these special functionality. Okay, so we just have a simple static caption here. So now if we rerun this report command, it will create the very same report, but this time it will add the SVG from the quality rule into our report. So now if we open our report again, you see that we have a new row here in the results table showing you the caption that we just stored into that file, a preview of the plot. We can also open that so that we can see it in a larger display, and we can download it like as the original SVG into our local system. And importantly, these files are included inside of the HTML. So this is just one portable HTML that you can email to your collaborators and so on. And there's no dependency. It doesn't even depend on an internet connection. So everything is encoded inside of that single file. So it's really like a portable, self-contained document containing potentially all the results that you generated with your analysis. Okay. So, but there's more to Snakemake that we can discuss, maybe a bit at least. So first, one important aspect that you might have noticed already, as you see here in these rule definitions, like here, output map/sample.bam, I tend to reuse these strings like in every rule, just basically typing them again or copy pasting them. From a just plain programming perspective, this is at least at the beginning a bit weird, because usually like the goal when you program something is that you want to avoid redundancy like that. So with like plain Python programming, you would probably just define a variable at the beginning containing the string, and then you would refer to the string 2 times, for example. This is possible with Snakemake, so I could refer to a variable here. But actually, it's in case of workflow definition, the goals are a bit different to plain programming. So as I said, with plain programming, you want to avoid redundancy. So that's very important. It's, of course, also kind of important for readability. But in case of workflow definition, it's actually a bit different. So there, the highest goal, at least in case you are defining your workflow in a human readable language like you have it with Snakemake, the highest goal is human readability. So in this case, the ability of somebody who just wants to look at your workflow to like read through the steps you have here, like scroll through them and immediately assess what they do, what they create, and what they need to create these. Like what are the input files, what are the output files, and so on. If I now would start defining variables here at the top and reusing them all over, this would hamper the readability because rules lose their kind of self-containedness, and it's harder to like immediately understand what's happening here. So therefore, we can sacrifice some avoidance of redundancy for the ability to have more human readable workflow definition. So that's why I tend to advise people to allow some kind of redundancy in the definition of input and output files in order to have it more readable. Okay, something else. So usually you would never write it like this because this is kind of specific to your data analysis and you don't want to have that inside of the workflow definition because you want to make it easy for the user to adapt an analysis to, for example, a new set of samples or something like that. So Snakemake allows you to avoid these kinds of definitions by having a directive config file. It can point to a file, again in YAML format. Can move this out and create this file here, like this. Inside this file, we have a key samples A, B, C, for example. Okay, and then in our code, instead of assessing a global variable samples here, we access another global variable that is automatically created by Snakemake if you define this config file directive here. And this is just a dictionary containing the content of this YAML file, which means that this dictionary will have a key samples, and under this key samples, you will have a list A, B, C. Okay, so this is equivalent to what we had before, but it allows us to separate the definition of the workflow from the definition of our particular analysis with particular samples, so that somebody who wants to apply an analysis to a new set of samples can just modify the config file. The same applies, of course, to also all kinds of other keys I want to put in here. So I could like put some arbitrary parameter here. I don't know, with some value, and then I could access that parameter from any of the rules here via the same syntax here with config and then the key and so on. So this can be very flexible. And as I said, since this is all an extension of Python, it's not limited to these config files. You could also read these values from SQL. You could read them from a TSV file, from a CSV file with Pandas and so on. Okay, so something else. So Snakemake also handles your is able to handle whether results in your workflow are intermediate or final results and do that in a proper way. So for example, the mapping here creates a file like sample.bam here, which is used again here to sort it. So we do another transformation to that file, and then we just use always the sorted file. So we don't actually need this initial BAM file here, okay? We can tell Snakemake to mark this as a temporary file. If we do it like that, Snakemake will, after this file is not needed anymore, so basically after this file has been created, it will be able to delete this output file and therefore save disk space, for example. We can even go one step further. In some cases, it's possible to define that the output of one rule shall be just directly piped into another rule. And this is possible, for example, in this case. So we have this BAM file created, and then we just read that via this sorting command. And basically, this just reads one time through the file. It doesn't need random access and so on. So instead of defining this as temporary, we can also define this as a pipe, which would mean that Snakemake would execute this rule together with that rule for a particular sample. And it would just, in terms of Unix, it would create a named pipe for this output file, which this shell command then writes to. And at the same time, this shell command would read from that pipe. And the actual contents of this BAM file will never be entirely on disk. And yeah. So in that context, we should also speak about execution. So Snakemake is, of course, not limited to executing on a single workstation. You can execute the very same workflow on a cluster system or on several cloud providers. So on the cloud, it works via Kubernetes, which would work with Amazon and Google at least. And cluster systems, basically all of them are supported. So via a generic interface. So this means in a cluster or cloud setting, Snakemake would ensure that, of course, the jobs from this rule and this rule for a particular sample, in case we pipe between them, they are automatically submitted together by the system to the same physical node, so that we can do this piping not via network, but just via the memory on that node, which would be very efficient. Okay. That's it regarding execution. Then I wanted to mention the deployment again. So as you've seen here, I've concentrated on deploying software stacks via Conda. Snakemake is not limited to Conda. So instead of defining like Conda environments like this, you can also define containers via the so-called Singularity directive. Singularity is an alternative executor for Docker containers. And it can directly use the Docker registry. So we could say, for example, Docker, I don't know, some container. And usually it's a good idea to specify the version of the container, for the same reason why we specify like the version of the tools here, because otherwise tools inside the container could change. So you might have something like this, I don't know. And then we could, at the command line, so for creating a certain file, we could tell Snakemake to not use Conda, but instead use Singularity, and then it would use the container instead of Conda. Okay, but it goes further than that. It's not only able to use either Conda or Singularity, it's also able to mix the two. So imagine that you define your software stack for the individual steps like this via Conda, then you already have a large amount of reproducibility in the sense that you get exactly the software you want in exactly the versions you want, but you don't fix the actual operating system these are executed on. However, this is possible via a global directive, again, via Singularity. So you can define a global Singularity container like this, and then some container. And if you now would execute Snakemake with, as you can see here at the bottom, use Singularity, use Conda, it would actually create all these software stacks for the individual steps inside of the container. It will still be stored on your local hard disk, but the creation of them and the download of the packages will be for the operating system and architecture defined by the container. Which means that you can basically use Singularity to fix your operating system and use the ability to rapidly define these environments, which is actually much faster than defining a Docker file and uploading it to Docker Store and so on. Use the repeatability of defining Conda environments for your actual software stack. And by this, it's kind of allowing you to use a sweet spot between the two technologies to very rapidly draft your analysis. And also it allows you to execute an analysis that was designed, for example, on Linux, on a different operating system like macOS, while still using the same underlying Linux via the container here. The only requirement for this Singularity and Conda integration or combination is that this container has to contain a Conda installation. Therefore, you usually use the mini Conda container provided by the company behind Conda. So could do it like that, mini Conda 3. Okay, so this is actually a Debian container that just also additionally contains the Conda command, which allows Snakemake to initialize these environments inside of the container. Okay, yeah, so Snakemake has a lot more functionalities that I don't want to cover in this short live demo. So for example, it allows you to replace these shell commands via so-called wrappers. And these wrappers then represent like unit tested modules that you can reuse between different workflows. There's also a central repository for these wrappers that allows you to share them with your colleagues. Let me switch to the slides again. There are a lot of resources available for Snakemake, like, of course, the homepage. The homepage contains an official tutorial, which is kind of usually a one-day course. If you do it on your own, it's usually faster, so maybe like 2 to 3 hours at most if you follow all the individual steps. It has some overlap with this live demo, but it will tell you a lot of details and give you a lot more additional functionalities yet that you can use and a lot more insight into how Snakemake works and what you can do with it. So you can do much more than I've shown now in this live demo. You can like redo this entire live demo with instructions on the Catechol scenario that I linked here. Importantly, if you intend to develop your own stuff with Snakemake, there are best practice workflows. They are all centered around bioinformatics, but still, even with knowledge, with no knowledge about bioinformatics, they will give you some insight into best practice patterns, how to encode like configuration files, how to define sample sheets, how to like modularize your workflow, and so on and so forth. Yeah, and with that, like I would just like to thank the community of Snakemake. So we are not only a huge user community, but it also has a large developer community from all over the world. So it's not me alone who is developing Snakemake. It has an active core team to whom I'm very thankful, and a lot of contributors who have generated a lot of features that you've seen today. And yeah, I'm really happy about this entire project and really thankful to the community. So thank you.
Thank you very much, Johannes. So I have a few questions for you. So the first question is about fault tolerance. How does Snakemake handle faults during the execution?
Yeah. So speaking about shell commands, it will just check the exit code and it will check the existence of the output files. If one of the intended output files is not present, the rule will fail. If the exit code is non-zero, the rule will fail. And in case of such a failure, it will stop executing downstream rules of that particular rule. It will still go on with everything that it has already started, but it will not schedule new stuff. But you can tell it at the command line to just go on with whatever it can. So there's this keep going flag that allows you to do as much as it can and only fail in the end. So basically, every failure is recorded in the central log and outputted at the terminal, and you will then be able to fix the error or try to find out what's wrong. Just redo that particular rule or tell Snakemake to rerun from that point of failure and so on. So this is all handled by the avoidance of redundancy, basically.
Okay, thank you. My second question is about the competitors. For example, you know yourself, like there is Make out there. How would you convince a Make user to switch to Snakemake?
That's a good question, because actually I was a Make user before I started developing Snakemake. So we used Make for all our data analysis in the lab, so back in 2011 actually. And yeah, so we reached a point where it was actually not feasible anymore. So when you have complex analysis, you quickly run into the situation where you have steps in your workflow that don't create a single output file, but create multiple output files. that would be the first thing that you cannot easily do with make. So you cannot encode that in make syntax. Second thing, you will end up in situations where you would like to use multiple wildcards in the same output file, like one encoding the sample name, the second, for example, encoding, I don't know, some kind of parameter and so on. And this is also not possible with make. And then Snakemake has all these additional facilities that make your life easy. So first thing, it has these data provenance features. It has these extensive abilities at the command line to re-execute. It has built-in support for all the different architectures like clusters, clouds, and so on. Finally, something that is for me most important, actually, data analysis is not only about quickly executing your code or doing it in an automated way. It's most importantly to me also about readability. But because in most cases, when you publish a data analysis or some kind of biological or in whatever field findings, I know it's not usually done, but this is how it should be done. You should deliver the code of your analysis together with the paper. And usually people will not be able, at least in nowadays where data is so big, they will not be able to just re-execute everything in order to see whether this works. They could with Snakemake, so they could easily without setting up anything, because it will, if you follow the guidelines I gave you today, it will basically deploy everything automatically and so on. But most importantly, in many cases, it will only be possible for people to look up in the code what you actually did. And usually, like a method section in a paper is not enough to specify all the details. And there will be some point where people want to look what you actually did. And for that, it's important. It's super important to have something that defines your analysis that is human readable. And this is not always the case with make, because you all know that it has this cryptic syntax of accessing input and output files inside of a rule. And this does not mean that this is not good. It's great for compiling stuff and for the things it was built for. But for data analysis, it's important that anybody who even not knows the system is able to see what are the steps and what did the people do, and that it's a modularized thing that you can easily just look at certain aspects and so on. And this is what is supported by a system like Snakemake, and that's not the case for Make.
Yes, thank you very much. Actually, the readability of Snakemake files is the feature that I wanted also to highlight, that I could understand the Snakemake file, even though I didn't know about them before. So my final question is about the new features that you are currently working on. Are there some features that you'd like to mention, or you think that are so cool that people should wait
Yes.
for them?
Yeah, of course. I mean, so one thing is already done, but it's very recent, so probably not everybody knows yet. So Snakemake since this winter supports data-dependent conditional execution, which means that you can write rules in a way that they wait for certain results to be present and only after those results are present, you can evaluate them and rewire basically the graph of jobs. So for example, depending on some result, you might want to skip certain steps or follow different paths in your graph. And this is now all possible via this data-dependent conditional execution and handled on any platform that Snakemake supports automatically. That's, I think, one important feature that makes many steps a bit easier. Although you should still use that feature with care, because in many cases, you don't need that. But there are certain cases where this can be very handy. So for example, clustering, where you don't know the multiplicity of the output files. So in case you don't know the K before the clustering, and you want to do like a whole set of downstream steps on all the output files of the clustering. And via this conditional execution, you can do that very easily and still in a human readable way. Regarding new stuff, what's coming next, or at least this year somehow, will be integration with Jupyter notebooks. So similar to the script directive you have now with Snakemake, you will be able to use a Jupyter directive, which you give basically the path to a notebook, and then Snakemake will allow you to first like when it's not there yet, dynamically build the notebook for a particular input file, like for particular wildcard values. It will store it in a way that it's automatically generalized to other wildcard values. So the same notebook can be reused then for different jobs of the same rule. And yeah, so, and you can do all cool things that you can with Jupyter then inside of Snakemake. So by just using Jupyter notebooks as a step of Snakemake rules. And the last thing I want to mention is resource usage. So Snakemake, I didn't mention it in the live demo, but Snakemake has awareness of the resources that every rule uses. So if you don't specify it, every rule will use for Snakemake one single thread. You can tell it that Snakemake will that the rule uses more than one thread, like 8 or 16 threads, and so on. It has a scheduler that is aware of these resources and can allocate the rules according to your constraints. Like, for example, you tell it that it only shall use 20 cores, then it will ensure that the rules that it schedules never exceed that number of cores. And this concept extends to not only threads, but also things like memory usage and so on. And currently you have to specify these things like memory usage or disk I/O prior to execution. So you basically have to know what is the mapping between threads and input file size to memory usage. In the future, Snakemake will be able to learn that from previous executions of the same rule. So for example, from the execution from another sample. So this would be kind of a machine learning problem that we are trying to solve currently. So this will make the annotation of resources in Snakemake even easier.
All right, thank you very much, Johannes, once again. We don't have any more questions at this point, so let's switch to the final slide. All right, so once again, thank you to Johannes for a wonderful presentation. I hope those of you who are Make users will think about switching to Snakemake, and those of you who are already Snakemake users will consider contributing maybe to the project. Our next webinar is scheduled for next week, and the webinar title is the SDE, a General Computational Chemistry Software Framework, and it will be presented by Ryan Richard. With that, I'd like to thank Johannes and all of you for joining us today, and we'll see you again in the next webinar.